Picasso, take us in. Full impulse. Engage HyperAF drive. Hey, welcome to AstroAF. I'm Doug. Really appreciate you stopping by. I hope you like that intro. I spent a huge amount of time on it, like 4 days, because I'm not very good at that kind of thing. Anyway, it was a lot of fun. I hope you enjoyed it. Today, I want to talk about this imaging system that I have, what I named HyperAF, and it's the fastest imaging rig I have ever built. Well, disclaimer, it's the only imaging rig or optical train that I've actually built myself. So I wanted to share this with you today. And actually, the impetus of this project, it started a year ago. And a little over that, I had purchased my Celestron EdgeHD 8, and the EdgeHD 8 is a highly configurable and versatile telescope. It is 32 millimeters at native focal length, and if you add a .7x reducer, it's 1422 millimeters in focal length, and it runs at f7 there at the native focal length that's running at f10. But it has one more configuration, and you may be familiar with Hyperstar, which is a Starizona commercial product, and that will allow you to run your Celestron telescope, the SCT in this case, at like F2, and they have another model which is f1.9, and that gives you a focal length of around 406 millimeters. And which is great because that's 3 configurations for one telescope with 3 different focal lengths and f ratios. And I had been doing some researching out on like cloudy nights and across YouTube and stuff, and I did run across some information on doing DIY Hyperstar, and I thought, it's kind of crazy, it'll probably not work, but let's do this as an experiment and let's see how it turns out. And so anyway, the idea is you remove the secondary mirror and you replace it with this imaging train right into the corrector plate with the camera system, and you need to take into consideration the appropriate field correction, and that gives you a much wider field of view. When I first imagined this, and I thought that I could maybe do a truly high-speed imaging system and what that might look like, I didn't expect to end up building something that feels like it belongs, in the enterprise. But that's what HyperAF actually is, and it's a DIY imaging project that it's really streamlined. It is aggressive. It flies through light years of cosmic photons like crazy. I mean, to the point where I was getting more data than I could process fast enough because I could do so much. In one night, I did a 9-panel mosaic of the Cygnus Loop. I had 8 hours in it. And then, I've done other things like in quick projects in one night sessions, of just a few hours, I'm getting enough data and signal that I have a finished image that I can process. That's what HyperAF is all about. A project that I started out with, like, everyone else, looking at the Starizona Hyperstar. And and don't get me wrong, that's a great piece of gear. The justification of the pricing was really a cause for pause, and because it is an expensive piece of kit, and so again, so that was part of the foundation reason for trying to get into it, because I thought, if I could do this myself, I bet I could do it for a lot less expensive. and have fun and learn about something in the process. And so I started in on this DIY project. So in this video, I want to talk about HyperAF, what it is, and its configuration, how it works, and what makes it such a unique entry into my kit. And you also find links and stuff to the parts, some 3D printed accessories that I've come across or that I've designed, and the components that go into building this. So if you want to do it yourself, you certainly can, and you can do it fairly inexpensively. Like, depending on what you already have, you could do this for $200 or less. So that would save you about $800 over the commercial product. And if you already have what you need here, it could be close to free. So with some 3D printed parts, and that's about it. So we'll go over it. So HyperAF is my name for a hyper-fast, wide-field imaging configuration that I designed for speed and simplicity. And it's truly simple. It just comes together, and it's lightweight, and it packages well, and I can take it and travel with it easily. And in this case, it's designed around the Celestron EdgeHD 8. I don't know that this would work on any different telescope. However, you could potentially try this on like a C8, so it might potentially work on that. And again, for probably $200 or less, you could do this DIY project. So this configuration is perfect for faint molecular clouds or dark nebula, which you saw in the intro was LDN 700, and that was a primary test subject. And then for doing the lightning fast mosaics, like I'll show you here in a little bit for the Cygnus Loop, it just works fantastic. So, but let's go over the imaging train here, and I'll talk more about it in detail. All right, so imaging train. The primary telescope is my Celestron EdgeHD 8 in this case, and I've got a reducer field corrector, and this is a required component in building this DIY setup. So it's a 2-inch 0.95x reducer coma corrector, and it's perfectly matched. It works really well with this setup. It's marketed as an F3 coma corrector, but as it turns out, it works perfectly fine, and it ends up giving me a f1.9 ratio, and that's calculated by, and I'll throw this up on the screen, the f ratio equals the focal length divided by the aperture. And then so the focal length here in this case is 388 millimeters divided by 203.2 millimeters of my aperture, which gives me an f1.91. So how did I derive the 388 millimeters? I arrived at that with basically 400 millimeters is where we end up with in a standard times the 0.95 for the coma corrector. That gives me the around 388. It's actually like 406 millimeter times 0.95. But anyway, it's right in that area. So, and then additionally, I did some plate solving in Nina and some testing with some different focal lengths on that, trying 406, trying 400, down to like 379 and 388. And the solver actually did best at 388. And so I used that as just an additional kind of backup to confirmation that 388 was the correct number on that. The entire system that I use is a like a ZWO ASI533MC PRO, and this is tested. I've used it a ton over the last year. I also have tested with the Player One Mars 662M planetary camera, and with this on lunar imaging is a beautiful matchup with the HyperAF. I intend to use the Player One Artemis-M Pro that I have, and I see no reason why it wouldn't work. I have a filter drawer in here. This is a ZWO 2-inch filter drawer, and that allows me, in this case, with the OSC camera, I've got UV-IR in here now, or I can throw in my dual narrowband. With the Mars, this is a mono planetary camera, or with the Artemis-M Pro, then I could just use the filter drawer for swapping out my mono filters for LRGB and narrowband filters, for whatever the purpose may be. So field rotation is dead simple. All you do is rotate this in the corrector plate to get your rotation. It couldn't be easier. So let's talk a little bit about the build and design on this. So one of the most important parts of the system is this little adapter right here. And it's very simple. It is a cylindrical adapter, and it has a flange that fits down inside the corrector plate with a shoulder on it. And this shoulder catches the ring screw that comes down and screws this down to the corrector plate, and then that holds this firmly. Then the HyperAF unit just slides into that adapter plate like such, and then I've got a couple screws here that I can tighten up and secure that in position. And then when I want to rotate it, I can just loosen these screws and rotate the assembly. One important thing to note here is I have the shim, and so when this is in the corrector plate and I've slid this down, what I discovered is that when it was pushed all the way up, I have a shim in here right now, and when this was pushed all the way into the corrector, the backspacing was incorrect. So I do have the 55 millimeter backspacing here from the coma corrector to the camera sensor, but the backspacing of the coma corrector with the secondary mirror was off, and so the collimation it was bad, and I wasn't able to get prime focus. So what I did was I just started looping images, and I started pulling the assembly out of the adapter until I got perfect collimation and prime focus. And I took my calipers and I measured that distance right there, which happens to be 5.5 millimeters. And then I just simply 3D printed some 5.5 millimeter shims and then slid those on. Those stay, and that allows me to remove and replace the assembly and have it exactly in back focus every time, and that works really, really well. Now, with the planetary camera, it has a different back focus from distance from the plate to the sensor. It's almost double what the 533 is, and I guess that's kind of typical with like planetary cameras. And so what I simply do there, and actually worked out, is I just added a second shim to push that out a little bit further, and that gave me the correct back focus spacing for this camera. So every camera is a little bit different, and so you'll have to figure that out to determine what the actual back spacing for your camera is. But it's dead simple, and it only takes like 20 minutes or so to print a shim, and it's no big deal. So yeah, so the camera and the assembly is mounted with the custom 3D printed adapter. And one other thing I wanted to mention about the adapter is that you might think that you'd print it in this orientation and that would give you layers going in this direction. Well, since this sits in the corrector with the weight of the camera and everything on it, that would be putting pressure pulling away from the layers with potential for delamination. And so I thought it better to orient it in the printer such as this, so that it printed across this way. And that actually took a lot longer for printing, but now the layer laminations are going in this direction with the direction of the camera and the way that it would pull. So that makes this PETG print much stronger than if you did it in this orientation with your layers going this direction. Because if they did and you were pulling, then you would be pulling apart the layers. So I'd recommend printing it in that way. Yeah, I'll have an STL for this, and I've got attribution. This is not my design, and I've got a link to attribution in the description for this. For cable management, so there's cable management in this type of configuration. is really important because the camera is in the center of the light path. And so what you want to do, rather than running cables down from the camera and straight across, is you want to run an arc. And this is a little 3D print that I got off either Printables or one of the others, but I'll have a link to it down in the description. And so this has a little slot here that fits over the outside of the tube of the Celestron and slides down onto it. And then this arc extends into and over the corrector plate. Now, the cool thing about the arc is that it kind of diffuses itself and doesn't cause any diffraction or anything within the light path. If you take a cable and go straight across from the camera and across the objective, you will get diffraction from that. But it's pretty neat, and it does work. This design right here prevents that diffraction from happening, and this thing ends up being pretty much invisible in flats and in the images, of course. And so it works really well. I've got my cables attached here with little black zip ties. I did it all in black for no reflection. I put the heads of the zip ties up so that they are not sticking into the light path at all. And, other than, they're just right on top of the cable manager here. So anyway, there's an STL for this too, and I'll have some images coming up showing you how these put together. So yeah, don't use a flat or straight cable run to go across the front of the telescope, because that's going to create like linear diffraction artifacts and unwanted spikes and streaks and so forth, and can give you some hard vignetting of or shadowing, of your cables. And so the arc gives you a much smoother path for your cable runs, and it prevents from having any of those linear diffractions and things like that you would get if you ran it straight. And this is also mounted inside the dew shield, and so it gives a nice area for your cable run. Again, links for that down in the description from like Printables, I think it was, but it might be one of the other ones. So yeah, the entire system, it's all pretty much contained here, and this is all screwed together, and it's very light, and it's a rigid system, and it's really, really nice for just quick changes. This can be installed in just a matter of minutes easily, and so it's not a big lift for setup time and things like that. And what's beautiful is there's no guiding needed for this. So I'm normally exposing at about 30 seconds with this rig. Depends on light conditions. So if I'm in darker skies, 30 seconds. If I'm in my backyard, it's probably maybe 60 seconds. And I've actually tested this up to 300 seconds. And I even did some higher ones unguided. So really, you're only at the limitations of the accuracy of your mount guiding or tracking, rather. But this, it gathers light so quickly that going for longer exposures like 300 would not necessarily be practical with this rig, because it gathers so much light so quickly at f1.9. And so I have found, just depending on sky brightness, in my Bortle 6 is 60 seconds is a good one, and Bortle 3 and lower, 30 seconds. I've done 10-second exposures with this in Bortle 1, and it kind of blew me away just how much signal it's actually grabbing. Again, I've been using this, as far as performance goes. I kind of hit on it there, but I've been using this for about a year now, and it has really changed how I approach my wide field imaging with my Celestron. And the LDN 700 image, that went really well. I used the 533 with that. That was in a Bortle 3 in Colorado. I have a video on that for my Colorado trip vlog, and you can check that out if you want to. It's a perfect example, that image, of what the system is capable of. It handled the dense star field and high contrast dust lanes of the dark nebula, and even got IFN, and yeah, I was really impressed with how it worked. Because this runs at f1.9 with an effective focal length of 388 millimeters, it lets me gather a ton of data in a very short window, as I mentioned. So, and that's critical for narrow imaging gaps when you just have a little bit of time, you're traveling and things are limited. This can get you the acquisition that you need in the short time that you may have available. So not just field of view, but actually working with your imaging time, if you're traveling or it's a break in the weather and you're just trying to grab something. So this can help out a lot. So I learned a lot with the system and working with it over the year and building it. It was fun because I presented this on my members only over in Discord, and which, by the way, if you'd like to join, I have a join link in the description, and members get perks and access to early videos and images, or if you prefer, buy me a coffee, you get almost exactly the same perks there, and you get access to the Discord as well. So with the system, even a millimeter of error in this backspacing can throw off your stars. So it is super picky at f1.9. So time taken in getting this backspacing correct is critical. And this coma corrector is the only one I found that'll work with this. So I've got a link for it down in the description as well. But yeah, this is the Sharp Star. Determining that back focus was just a manual process of looping some images and moving this out of the adapter until I got prime focus and collimation. And then I measured that and figured out this adapter size. So once I was able to get that pinpoint focus and sharp stars and got this measured and this then becomes a drop in, and it's right every time. So it works really well. I leave this entire assembly together other than the camera. I'll swap it out, but this whole system stays together. I never have another need for the filter drawer other than this system. I've got a spacer in here to get my backspacing, the filter drawer, and then depending on the camera, I may add or remove one of these spacers, and that's it. Tested with the ZWO ASI533MC PRO and also with the Player One Mars-662M. And I don't see any reason why the Player One Artemis-M Pro wouldn't work. I don't know why it wouldn't work as long as you get that spacing correct for your sensor. The shim, it should work with just about any camera. I think your only limitation would be if it's a really large camera and you might be getting out into your light cone area. So that would be a consideration. You want to keep this as trim and thin as possible. So final thoughts, this thing, it kicks butt. It kind of represents my philosophy of trying to in this hobby of just experimenting and trying to learn stuff and do stuff and try to save money where possible, and it's end up as much of an image train rig that I use all the time for maximizing light, and it's light on weight, and it has turned my gear into something more than just the sum of its parts, really. And it's expanded the versatility of my telescope. I basically have 3 telescopes in one now. So for me, that's been the biggest win for this system, and I've just had a lot of fun using it. So again, down in the description, I've got resources, links for all of this that goes into doing this DIY project. So if you want to take it on yourself, you could do it for $200 or less. I actually got this coma corrector secondhand off of Cloudy Night, so I got it for less than what it would cost new, and that worked great. If you already have that, then you're in for basically free. That's assuming, if you're into astrophotography, you already have a camera and you probably already have a filter drawer and a filter. And, so if you got those things, then this is a $200 or less project to get f1.9 wide field imaging going on your Celestron EdgeHD 8 and potentially on your C8. I haven't tested that. I've got some friends with C8s and they were curious about trying this out. So if you do try this out, let me know. I'd love to hear it in the comments, and I'd love to have you join as a channel member to get more information like this and pre-release. And hey, subscribe if you're not already, because then you'll get notifications of future videos. Hit that bell. Anyway, I really appreciate you. Thank you very much for stopping by. And yeah, let me know if you have any questions. Oh, the community tab is now open to subscribers. So if you are a subscriber, you can now post your own conversations on my community tab. You can post your own images. And we can talk about those things as a community. And if you have questions about, this HyperAF image train, certainly go ahead and post it in the community, and we can have a discussion there. And then also always ongoing over on my Discord server, and the link is in the description. All right, thanks so much. My name is Doug. This is AstroAF, and you have a great day. Here's some images from the HyperAF rig.